Hello everyone, good afternoon and welcome to another installment of the Leaders for Global Operations Web Seminar Series. Today we have Leon Glicksman, Professor of Building Technology and Mechanical Engineering with the School of Architecture and Planning and the School of Engineering here at MIT. He founded the Building Technology Group at MIT 23 years ago. He has carried out research on natural ventilation, thermal insulation, and software tools for energy-efficient design, and he is a member of the Energy Council of the MIT Energy Initiative. For your note, there will be a Q&A session at the end of the presentation. If you would like to ask a question, you may use the chat window to post the question to everyone at that time, or during the presentation, and it will be read aloud at the end. During the Q&A session, you may use the chat window or the raise your hand button located at the bottom right of the attendees panel, and you will be unmuted to ask your question aloud. With that said, I would now like to hand the presentation over to Professor Glicksman.
Thank you, Steve. Interesting concept to be talking with an unseen audience here. I hope you do give us some feedback and questions at the end of the session about any of the things that we talk about today. What I want to talk about today is issues related to energy efficiency in buildings, an area that I've been focusing on for the latter part of my career here at MIT. And, well, the reason, obviously, we're concerned about it has to do with the issues of energy independence as well as global warming. I'm sure you've seen this, this slide many times from Al Gore and other people talking about the raise of the CO2 concentration in the atmosphere, a lot of it associated with the burning of fossil fuels for our development since the really start of the last century. And what we need to do then is start thinking about some solutions for the problem of energy. And the traditional solution focus is shown here on the next slide, which shows really the flows of energy. These are the energy inputs on the left-hand side here, coal, natural gas, and the like. This is from the Energy Information Agency. And on the right-hand side are how the particular are used. And in between, we have electrical generation occurring in this central region. So as I said, a majority of the concerns have really been how do we increase the production either with renewables or innovative ways of developing fossil fuels, which we can use for a number of these situations. And the quandary we're facing, I think, is best illustrated by an old story I heard when I was an undergraduate here at MIT some years ago, in 1801, which is the introductory calculus course. And it turns out that in the calculus course for the undergraduates, they have a number of hour exams which they give the students. And in examination number 2, the professor entered the room, passed out the exam booklets. The students looked at it, and all of a sudden one of the students waved his hand on the air and said, "But professor, this question number 1, this is the same question you had on the first examination." And the professor stopped for a second and said, "You don't have to worry, I've changed the answer." So I think that's the situation we're faced with here, was the fact that we have this problem, but we really have to look for new answers which we can use to solve some of these. And the focus of what I'm going to talk about is what do we do at the other end of this energy spectrum when we start looking at how the energy is used. So if we can substantially reduce the right-hand side of this diagram here and reduce some of these demands, we can go a long way towards solving some of the problems, both in near term as well as in long term. So I want to talk about some issues which are related to the economics, the technologies, incentives, and then give you a flavor for some of the kinds of research we're doing on the technology side to help solve some of these problems of energy in buildings. So the outline of what we're going to say is that energy efficiency is an important solution for these problems. It can be cost-effective, and in many cases, much more cost-effective than a number of other solutions people are looking at. We need an integrated approach. We need new contributions, both technologies and tools, and there are a number of challenges we need to meet in the future in this field as in others. So again, to start out with, it turns out that in the U.S., if we look at the primary energy use and where it goes in the economy, almost 40% of the total primary energy in the U.S. is used in buildings. Now, this may be fossil fuels directly used, say, for heating buildings, or it may be the amount of energy which is required for generating electricity, which then again is used in buildings. And again, just to remind you, almost 3/4 of all electricity generated in the U.S. is used in buildings for functions, for appliances in buildings, and for the various functions of the building. We also have to keep in mind, if we come up with some solutions, we have to consider issues like indoor health and indoor well-being of people. And so we can't do things which are going to cause problems from that aspect as well. Just to get an idea of where the energy is used in buildings, it turns out that the largest energy use, as you can see in this pie chart, is space heating. Almost 1/4 of all the energy in buildings is used for space heating. Lighting is second, space cooling third, and so on. And some of these sectors are going to change as time goes on. So in commercial buildings, focusing on that rather than entire building stock, it turns out that the largest energy use is for artificial lighting used in the building. And later on in the talk, I'll give you some ideas of ways we can substantially reduce this energy use and in fact turn the lights off in many cases. Space cooling, you can see, is also an important aspect, and as we start growing in the southern part of the U.S., as well as in developing countries where the climate's rather warm, space cooling is going to become a larger share of the total, which we'll see in commercial buildings. And another one I need to point out is the electronics, which you can see over here on the left-hand side. Right now, it's less than 10%. One of the largest increases, one of the fastest increases, I should say, for energy use in that field is for data centers. These are the large installations that Google and other people have, which service the people's need in IT. Right now, the estimate is that 2 to 3% of all electricity in the U.S. is consumed in the data centers for running the computers as well as for keeping the computers cool. And the predictions are that's going to grow very rapidly in the future. Now, at the same time, we need to think about what are the physical limits. Obviously, we can't violate the laws of physics, and there are some examples in commercial buildings that we'll talk about. For example, people hear about green roofs or cool roofs. What will that do, actually, to save energy in buildings? There are some issues people are talking about by 2030 that all our new buildings should be zero net energy on site, which means they have to generate as much energy as they use, so they don't have any net demands on the electrical network. And just to give you an example of some of the physical limits here, I've taken the John Hancock building and did just a little thought experiment. Let's assume that we try and make it zero net energy by covering the entire surface of the Hancock building with photovoltaics. So you can't see it out of the windows anymore. It's all photovoltaics on all sides of the Hancock building. And the question is, can we in fact make this building zero net energy by using that? Or what percentage of the energy used in the buildings could be generated by photovoltaics? Well, it turns out if we keep the building operating as conventional building, we could probably meet 15 to 20% of the energy needs of the buildings by using the photovoltaics over the entire surface. So what that tells us is, zero net energy may not make sense here, and in fact, if we want to go in that direction, we really have to seriously think about first reducing the demand for energy in the buildings before we start worrying about putting renewables on the buildings. And I'll have some more to say about that later on in the talk. Wind is another option which could be used, and again, we'll look at how well that might fit into some of the issues related to buildings. There are also obviously economic limits of what makes sense when we talk about the building sector and compare it with the costs, say, for generating electricity. These are some numbers I took from the MIT Energy Initiative study on nuclear as well as on coal. And what that says is, assuming there are no penalties for CO2, the cost for generation, this is just at the plant, this is not the cost for transmission or the like, the cost for generation of electricity is something in the order of 4 to 6 or 7 cents per kilowatt hour. So that's the basic thing that we need to compare it with. I'm not saying that's the way we should go, but that's probably the cheapest way of generating energy. If we look at renewables, it turns out wind energy in many instances can be economically competitive with costs ranging from maybe 3 to 8 cents. Biomass, if done correctly, again, is reasonable. As we start going down, though, and for example, solar thermal, 12 to 18 cents, and solar photovoltaic right now is in the range of 30 to 80 cents kilowatt hour. That's without government subsidy. That's just basically taking the initial capital cost and then prorating it over the life of the PV, asking how many kilowatt hours can we generate from the PV, and then placing the capital cost against this amount of generation. So right now, solar PV does not look economically competitive compared to the others. That's not saying that won't change in the future, and there's certainly a lot of research trying to reduce the manufacturing costs for that. We can also compare this with the cost of saving a kilowatt hour. So if I have a new building, we may want to invest some more money in the capital cost up front to reduce the energy demand. And if we look at what the cost of that is, and that's down at the bottom in advanced buildings, these are based on a study done in California, the cost of saving kilowatt hour ranges from nothing to 6 cents a kilowatt hour. Why nothing? Because it turns out in some cases, if we in fact invest more in energy efficiency, we may offset that cost, say, for better windows or better insulation by reducing the size of the air conditioning plant that's now required to keep the building cool. So that really, from a cost standpoint, looks like something which may make sense and we should possibly follow. And this is one that I'll spend a lot of time talking about here. There's also a fairly famous McKinsey report that did the same kind of thing, to look at what the cost of CO2 abatement is in the U.S. economy. And you can see that on the horizontal axis is the amount of CO2 which is saved. On the vertical axis is the cost, the real cost of doing these things. You notice zero, and some of these costs are negative, which means if you make this investment, you'll actually, over the life of the investment, save money. And you'll notice that in many cases, the things which appear on the left-hand side are things related to buildings. New shell improvements, new lighting, and the like. Whereas some of the things you would hear so much about, like photovoltaics and other solar things, are on the right-hand side, where there is, in fact, a substantial net cost. So again, the same kind of argument as the previous slides on this. So here we're faced with a situation. Building efficiency is an important solution, cost-effective and done properly. And I'll have some more to say about what's proper or not. And the question is, why don't more homes and more businesses adopt efficient measures? And there's a number of barriers which we have to overcome in this particular area. First of all, the building industry and the construction industry is one of the most conservative industries in the country. It just takes a lot to change them. The field is very fragmented. There isn't a Boeing or a Ford there which integrates the entire building production process. We have a number of different players, both from the supplier side, separate people that make lights, make windows, make air conditioners, make controls, and the like. Also, in many cases, we have the problem that the people who build the building and sell the building are not the people who pay the electricity bills. So the people who build the building, their incentive is to keep the first cost as low as possible so they can maximize their profits and let somebody else worry about the operating costs. Also, there's a lack of incentives. In many cases, there's not positive incentives for people really to carefully be exploring it. And as I said, there are a number of things which hold it back. One, obviously, is the issue of all the litigation. If we try something new and it doesn't work, we're sure somebody's going to take us to court and give us a hard trial. Also, there is the issue of education. A lot of cases, people don't understand what energy efficiency really means, and in many cases, if they do, they may be doing the wrong thing. So there's lack of information, poor performance projections, and what we call a linear design process, where the architect does his or her thing, and then when they get done with the major design and orientation of the building, hand it off to an engineer and say, now make it energy efficient. And in many cases, they've already foreclosed on a number of things which should be done in the building, say changing its orientation. This is another problem in terms of information, and what I've found from the literature are some data which show how LEED buildings, these are the Leadership for Energy Efficient Development, are different buildings. Gold, platinum, shown here is the best, silver is next best. They have a number of criteria. About 25 to 30% of the LEED points are for energy efficiency. And what we can see here is how the energy efficiency of these buildings stack up compared to the proposed savings. So the proposed projected savings are on a horizontal scale here. This is compared to a standard building. This is the actual measured savings. So if everything was wonderful, we would be along this straight line here where the measured and projected savings are about the same. And you can see some buildings actually do better than projected. You can also see some buildings doing worse, and in some cases, buildings which are actually having lower energy efficiency than just conventional buildings. So this kind of information and the lack of really a more detailed set of information for a larger group of buildings gives people pause when they start thinking about doing energy efficiency. One of the things that we found, and one of the most important things when people ask, well, what is the solution? The first thing to keep in mind is there is no silver bullet. It just, in the buildings field, there is not that one thing which is going to essentially make the building twice as efficient. In this case, as some people put, there is something called silver buckshot. We have lots of different things, lots of different reasonable solutions. We have to integrate them together if we're going to find a solution which makes sense for this particular kind of situation. Let me spend a moment just talking about the building technology program at MIT. As Steve said, we've been in business for about 23 years. It's a joint program between architecture and engineering. We've now built up to 5 full-time faculty members, 25 graduate students, and we do research in a number of different areas, particularly related to the next generation of technology, as well as to design tools which architects can use to do preliminary designs. And I'll give you a flavor for some of the things that we're doing on a particular program. First of all, we've been doing work probably for about the last 10 years on natural ventilation. The idea being in commercial and residential buildings, in many cases, Class A office buildings, for example, are now built primarily with sealed up windows and air conditioning year-round. It turns out if we have operable windows or other openings to the outside and carefully design the interior volumes so the air can freely flow through the building, we can find that for some or all of the time during the summer, we don't need to use the air conditioning. We can, in fact, allow the airflow from the outside to provide comfort conditions in the building. And numerous studies have shown that people in naturally ventilated buildings are much more comfortable and are more productive than people in the sealed up buildings that we normally think about. So we've been trying to do some work to understand what happens in a naturally ventilated building and look at some good examples. This is the Philip Merrill Environmental Center from the Chesapeake Bay Foundation. And this is a building which has a dual mode system, which means that in the spring and the fall, when the weather conditions are proper, the windows and other openings in the building are opened, and as the diagram, the artist's conception shows you, they're open so in fact we can have flow of outside air from one side of the building to the other to provide comfort conditions. Well, it turns out if you've ever lived in the Washington, D.C. area, clearly there's times in the summer this is just not going to work. The temperature and humidity are too high. Under those set of conditions, the building then is closed up and you use the conventional air conditioning systems. But for systems like this with the dual mode capability, what people have found is, and again depends on the particular weather conditions, in many cases you can save half or more of the energy you'd normally use for air conditioning. And again, as I said, the people are generally happier in this kind of environment. This is another naturally ventilated office building which we monitored in Luton, which is about 50 miles north of London. You can see the operable windows on the side here and on the top stacks, which are allowed then for ventilating the warm air that's generated within the building. This is a look at the interior of the building. One of the obvious things is it's an open plan space to allow the air to easily circulate. Also, you notice the ceiling is actually a concrete ceiling and is designed so there's lots of surface area, so there's good heat transfer between the air and the concrete. And the idea is, if we want to maintain comfort conditions in the middle of the day in this building, when the outside air temperature is the highest, what one does in this design is you open the windows at night, allow the air to circulate through the building and cool the concrete. Then in the daytime, that cool concrete helps maintain interior comfort conditions. So again, this is just a simple schematic. Night ventilation to cool the concrete, or what we sometimes refer to as thermal mass, and then in the daytime, the cooled concrete helps maintain conditions. And this is just some experimental data that we took in the Luton building in the summer, August of 2003, where they had a fairly severe summer, particularly for conditions in Britain. This line here, the blue line that you can see, is the actual measurements we made of outside temperature. And each one of these cycles is one day, and you can see in the afternoon in the summertime in August, the temperature got up to 40 C, which is above 90 degrees Fahrenheit. The other lines in here, though, show what the interior temperature are in different floors. And because of the thermal mass, you can see that the air temperature inside the building is about 10 degrees centigrade lower than the temperature outside. So again, the thermal mass, if properly controlled, can help to establish very comfortable conditions within the space. Some of the things we can learn actually from traditional architectural designs. This is the wind scoop, or sometimes called wind tower, which is used in traditional Middle Eastern architecture. And you can see a number of these towers poking up above the roof line of the building. And what these do then is provide a path for the air, the wind, if there is any substantial wind, to be caught within these, brought down into the building and circulated through the building. In many of the cases, they've also put various kinds of textile materials which are dampened with water in here to provide evaporation. The evaporation lowers the air temperature, and also the air now being heavier, since it's colder, essentially helps promote the motion of air through the building. Here's a modern use of this technique in the Zion National Park, and there you can see these towers here. Same idea, water is evaporated in the towers, it lowers the temperature and raises the density of the air, which then flows downward in the towers and out to the visiting center to provide comfort conditions through the summer. The only drawback for this system? Well, of course, it uses water. So it might be something you'd like to use in a hot, dry climate, but in places like Phoenix, Arizona, there just may not be enough water that you can use this during the entire cooling season. But it certainly will save considerable energy compared to the use of air conditioners as used in traditional buildings. This is an artist's conception of a building which is being built right now in Tokyo, and our group is working with the developer in Japan to design this both with natural ventilation and enhanced use of daylighting. So in this case, air is drawn in through this facade that you can see on this side with operable units at the top ends of the windows on each floor. And then the air is drawn through the cross-section of the floor, and then there are some vertical shafts or towers where, because of buoyancy effects, because the air is warmer, it rises to the top of the building without any use of any mechanical motions. This is a cross-section of a typical floor here. This is the entire cross-section. And these units, which I've outlined here in green on the right-hand side and the left-hand side, represent the footprint for these vertical towers. So the towers do not occupy a significant amount of the floor area, yet provide substantial enhancements in the energy efficiency. And again, our projections for Tokyo is we can save about 50% of the energy normally, which would be used for air conditioning of a building of this type. We also have developed some software tools. This one's called CoolVent, which allows designers, architects, and developers to get an initial handle on how a building will perform in terms of the temperature distribution and air circulation through a complicated building. So this is a cross-section of a building where we have like the Luton building, we have floors on both sides, a central tower in the center, so we have both wind and buoyancy promoting the flow of air through the space. We're continuing this work, and in fact now we're starting a new part of a joint new U.S.-China program to look at energy efficiency in buildings, and we'll look at the opportunities for using natural ventilation in the developing world as well as in the U.S. and Western Europe. We've also looked at other issues related to ventilation. This is a study we've done actually at MIT. I had an undergraduate who wanted to do an undergraduate thesis. We said, well, let's look at one of the buildings which uses probably the largest amount of energy at MIT, and it turns out to be the chemistry building. We looked around and tried to figure out why. The lights are left on all night, but it turns out the lights don't use that much energy. The culprit which we found which causes the most energy use are these fume hoods here. Turns out the building has more than 200 fume hoods. In many cases, the researchers left the fume hoods open at night. Now, the fume hoods are designed so that it's a fan that always pulls air from this conditioned laboratory space into the fume hood. The idea being, if you're running a chemistry experiment, you don't want any toxic fumes to drift back out so the investigator would come in contact with them. So there's all this set up so when these sashes, these sliding windows are open, there's a positive air velocity. Well, what that does in the wintertime means we're conditioning the air in this space. We have to heat out the outside air, bring it into the space, and now the fume hood is sucking that air in and then discharging it up the top of the building. Obviously, we can't recycle that air for safety reasons. Well, we did some back-of-the-envelope numbers to say, well, let's look at one fume hood. Let's assume that these sashes stay open for the entire heating season and ask how much energy is lost, the energy sucked from the lab into the space, how much energy is lost here, and let's compare it with a standard we could understand. It turns out one fume hood, the energy heating energy which is lost is equivalent to the energy to heat a single-family home in Boston. So one fume hood is one home. Well, once we put it in those terms, people could easily understand. All of a sudden, the head of the chemistry department got very interested in encouraging his people to do something by closing the fume hoods. Some later students developed some programs where they could actually give people, the lab directors of each of these labs, some feedback as to how much of the time their fume hoods were left open, as well as comparing them to other labs in the building. And once we got this feedback in place, the more people got much more diligent about closing these. Now, this is an example of actually the newest building on the MIT campus, and then this is a Koch Center for Cancer Research, which was just dedicated about a month ago. And what we found out in that case, and a colleague of mine, Les Norford, worked with some people from the safety office, is even when the fume hoods are left open, the amount of air velocity that needs to be sucked in for safety's sake was grossly exaggerated, and we could reduce that by 20% and still assure people of safety. So we've instituted that in the new Koch Center, which means a very substantial saving in energy, both the heating energy in the wintertime as well as electricity to run the fans. So the electricity savings may even be more than 20% for this particular building. So a good example where some very simple research is now already showed up as in new building designs on campus. Here's another idea for energy efficient buildings. This is part of what's called a passive house program. These are homes in Sweden, look very conventional from the outside. It turns out have some very different kinds of things. First of all, they don't need a central heating system. Why? Because in fact these walls are about a foot thick, and in fact they're filled with insulation. The windows are also triple glazed so that you get very high efficiency. In this case, they found that in most situations, the amount of energy which is given off by the residents of the building, as well as given off by the energy efficient appliances, is enough to keep the buildings warm. And this technology is spread now to northern Germany, and I'm happy to say now there's a few homes in the U.S. which are also using this passive house. If we want to look at more advanced things, there is something called aerogel insulation, which uses a way of nanotechnology to make very, very fine voids in this material, so fine that in fact it reduces the impact of any air which gets into the inside of this material. This is another view of some commercial aerogels which are available right now. And we in the lab are in the middle of a project to, in fact, improve the performance of this aerogel insulation so that about a ½ inch of aerogel will be equivalent to about 3 to 4 inches of conventional insulation. The hope is if we can make that kinds of things into panels, these could be easily retrofitted on the inside of existing buildings as a way, in fact, to substantially increase the insulation of the walls, but not at the same time cause major renovation problems. So it could almost be used as paneling on the insides of the wall systems. At the other extreme, we've done some work in northern Pakistan. The idea here is they have a number of buildings, for example, school buildings for children, which are totally uninsulated, so cold that in the middle of winter they have to close the schools because they can't keep the children warm. And we've looked, there's some straw which is available, a waste material, and we've done some work on essentially an insulation board made out of the straw. And right now, one of our former students in Pakistan starting a little startup company developing the straw, which could be used there, as well as in the shantytown areas around the big cities in Pakistan as a way of insulating the tin roofs which they use in the buildings to provide comfort in the summer as well as safety in the wintertime. Another concept that our group is looking at is the use of solar energy, but in our case, what we're looking at is can we use the solar energy to minimize the amount of energy used for lighting. If you remember, lighting is the largest energy use in commercial buildings. So the idea here is if I look at the solar energy on the outside, and we're looking now in the visible spectrum, the intensity is 10 to 100 times greater than what we need in the interior for proper lighting. So the idea is, can we develop some devices, fairly simple devices, which will bring the light deeper into the interior and allow us to turn off the lights. This is an example of one of these types of geometry. This is fairly complicated, has been originally set up in Switzerland and then pursued by one of their PhDs who were on our faculty. So the idea is you put this mirror-like device in the window, it captures incoming solar energy and projects it deeper into the room. There are two pictures here. These pictures are taken from the window looking at the interior of the room with no lights on at all. The left-hand side is what a conventional window will do, and you'll notice near the window it's fairly bright. In the back of the room it's fairly dark and you'd have to turn lights on. On the right-hand shot is the same picture, same room, but now with this device in the window which throws the light deeper into the space. Again, no artificial lights on, and you can see that it does very much better on bringing the light deeper in. There is a much more compact version of this which we've developed for that building in Tokyo, and we'll be deploying it in the top 4 or 5 floors of the building. Again, it's a way to substantially reduce the amount of artificial lighting which is needed in the space. Again, estimates are we could save up to 50% of the energy which they now use for lighting in those particular spaces. We've also done some work developing design tools. These are designed, there are a number of simulation programs already on them developed, some of them with your tax money, to try and in very detailed manner simulate the energy use in buildings. What we've done is say, well, can we do something simpler that architects and the like who are not specialists in these things could easily learn in about an hour's time and then use. And on the bottom there's 4 different scenarios, so that very easily they can compare the performance of those scenarios in terms of energy use and the like. This is a program which is online. People are welcome to use it, and the URL is just mitdesignadvisor.mit.edu. So it might be something you might want to try, and it allows you to try out different building orientation, different insulation levels, and the like. So this is one example where we've used this tool, and this is to look at what's the advantage of, in fact, changing roofs. Those of you who are in the energy field probably have heard a lot of talk about so-called cool roofs. So the idea is, for example, in a flat roof commercial buildings where we typically use bitumen roof system or a ballast system where the roof is very dark and absorbs solar energy, the thought is, well, instead of doing that, let's put a reflective surface to reflect that solar energy. or put a green roof on. Now, the idea of the reflective surface is it reflects solar energy, so less of it's absorbed, so in fact helps us from the global warming issue. It's also claimed to reduce the energy use of the building. So we use that tool, which I just shown you, and in fact tried out some ideas to say, well, how much does a cool roof help us compared to a conventional? So this is the case in Phoenix, Arizona, where again, most of the energy for comfort conditions is for cooling. And you'll see here, looking at the 3 bars on the right-hand side, and these bars are the annual energy use, kilowatt hours per square meter of building floor area. This is the total energy use for a conventional black roof. This is the energy use for a cool roof or a green roof. And you can see that there are some enhancements, the reduction of energy in that case. Well, the other thing we then said is, well, what about older buildings which have very little, if any, insulation in the roof? What's the advantage of a cool roof, say, as compared to just upgrading the insulation? So in this case, in the next one, we've looked at Boston, looked at a 3-story building, and now, again, what we've said is, well, this is the energy use. This blue bar here is the total energy use for heating, cooling, and lighting for a building which has no insulation. This is R value is a measure of the insulating efficiency. Higher R values means more insulation. So this first case here is the case where there is no insulation in the roof. And now what we've done in this case is we said, well, what happens if, in fact, I take this roof with no insulation and essentially put a cool roof on? So that's these set of bars here. So again, we have no insulation in the roof, and now I put a cool roof on. And you'll notice that, in fact, the energy use has stayed about the same. Although we still get gains in efficiency in the summertime, we're losing in the winter, because in the winter we actually want to absorb that solar energy. Now, at the same time, we can say, well, let's just stay with the black roof and let's add some insulation to an insulation level of about R17, which is about, I'd say about 2 or 2.5 inches of foam insulation. And you notice how much the total energy use has gone down. This is this red bar here. Now, if I do the cool roof and R17, that's this red bar in the second cluster, and you can see there's almost virtually the same result, which is telling us that if I'm starting out with a building which has very little insulation, insulating the roof of the building has much bigger effect on the energy efficiency than putting a cool roof on. And in fact, over here we have green roofs, which is the last cluster of bars over here. And we see the same kind of thing occurring here. That once we've added some insulation, whether in fact it's black roof or green roof, we're getting about the same result from this case. More recently, we've done a study looking at U.S. building stock, and what it says is if we're talking about old homes, 1950 to 1970, where the insulation level is fairly low in the attics of the homes, in many cases, adding insulation will have a greater effect on energy efficiency. And in fact, if we look at global warming, we'll have a greater effect on global warming, because as we reduce the energy consumption, we reduce the amount of CO2 that's going to be generated over the lifetime of those buildings. Now, there are still people talking about going towards zero net energy buildings. So I have another student who's looking at, well, if I want to do something like that, I really should be thinking about an integrated solution where I think about renewables, and at the same time, we think about energy efficiency. That's sometimes called negawatts, meaning we're reducing the energy requirement. So she did some studies on what's the optimum mix for a conventional building. This is but before that, this is an example of one proposed solution, and this is the Masdar development project in Abu Dhabi. This is going to be a development which ultimately has 70,000 people. Again, the goal is zero net carbon. So in times of the year, they'll be drawing electricity from the grid. At other times, they'll have photovoltaics to be returning excess electricity. So again, the idea is how much sense does that make if I apply it to more conventional building types? So here's an example where the student has done this trade-off, and what she did is a Monte Carlo kind of thing, where she looked at a number of different combinations of energy efficiency. and energy efficiency alone are shown by these green dots. Combinations where we simply use photovoltaics with no energy efficiency, and then the blue dots are a combination energy efficiency and photovoltaics. And again, the conventional starting point here is a building which has about 270 kilowatt hours per square meter of energy use. And you'll notice with some of the energy efficiency measures, we can substantially reduce that down to something approaching 100 kilowatt hours per square meter. The horizontal scale is the capital cost above the baseline of the building. And you can see that for some fairly modest increases in capital costs, we have substantially reduced the demand for energy. If I want to get to zero net energy, we've got to combine this with photovoltaics. And in this case, you notice we go way out here in terms of capital cost above baseline before we've got close to zero net energy. So this is one of the things we need to keep in mind. We can also look at this in terms of total cost. So this is the capital cost plus a net present value of the energy cost over the lifetime of the building. Again, zero is our starting point. And again, you'll notice with some energy efficiency, the total cost goes down because we're saving so much over the lifetime of the building, it more than offsets the capital cost. Whereas if I purely do photovoltaic, we're going in the other direction. And then finally, if we want to cross plot these, we have net annual energy here versus total cost. And again, you can see the sweet spot might be over here. If we want to get, again, towards zero net energy, we're going fairly far out in the total cost thing. So these are the things that policymakers need to consider when they start talking about for an entire community. What's the direction we should make to reduce our carbon footprint? And I would argue in many cases the best solution is not to design just new buildings to be zero net energy, but use some of those resources to improve the energy efficiency of older buildings and maybe make the new buildings approach 50 to 75% energy reduction rather than going to 100% reduction. Finally, and I'm just going to briefly talk about this, we have another student looking at how do we monitor commercial buildings. And in this case, what he found out is in many cases, simply the building is operated incorrectly. For example, he did one building at MIT and found out that for the air handler, which delivers the conditioned air to the space, the heating and cooling systems were both operating, so they were fighting each other, and substantially increasing the energy. Let me get beyond that. This is just sort of schematic of what the control for that for a large building at MIT looks like. This is the output of the software which he's designed, and the main goal of the software is to identify to the maintenance people what are the 10 most important things going wrong in your building, and then using probability to estimate what is the energy, what is the cost associated with that. So in this case, what I've circled down on the right-hand side here is just an output from that, which says, in this particular case, there's a 20% chance that you've wasted almost $6,000 or more per year because of improper operation of your equipment. In some cases, the cost is much higher. So again, the idea is take lots of complicated information, and most, say, large commercial building has hundreds, if not thousands, of measurements, and distill it down to something that the maintenance people can understand on the fly, which says, here's the 5 or 10 most important things going on. Here's what it's costing you if you don't start worrying about fixing them. And then finally, I couldn't finish without some comment about what's going on in the developing world. We look at China, it turns out that every year they're building 10 million or more new residential units. If we don't help them make those energy efficient, there's going to be a tremendous draw on both the energy resources of the world as well as a tremendous output of CO2. China has now passed us as the largest generator of CO2 in the world. This is an example of some of the older buildings. One of the mistakes you see people make is these buildings are originally designed with balconies. The people enclose the balconies with these, if you will, permanent window systems. In the summer, what they've essentially done is built themselves a greenhouse, and now the air conditioners have to work that much harder to provide comfort conditions in the building. Here are some new buildings, and again, you can see these open balconies in some cases, again, have been closed in. Same kind of problem that they're going to face. We also had a student do a survey of Chinese consumers to ask them what's most important when they think about buying a building. And no big surprise, transportation and location turned out to be the highest. And if we talked about green issues, they're way down here. In fact, they're off the scale here. Really not important. And we said, well, what kind of green issues, what kind of things would you think about? They said trees and grass. They were not thinking about energy efficiency. So it's one of the things we need to emphasize to the developing world as well as to ourselves. We haven't set a very good example, but hopefully, as they're doing this new construction, they can improve on what we've done. And in fact, one of the things we've done is we've edited this book trying to suggest some ideas which make sense within China. Well, one of the projects we did in China, we went to the project area with the developers after setting up a conference with them, and we found this banner hanging down from the side of the building. And for those of you who could not read this, in fact, they even had the one in English, which said, "Welcome MIT experts." And that's one I keep in my office, so when the dean comes in, I remind her that, in fact, we are doing some work that at least they're appreciated on the other side of the world. I think I'll stop here. Thank you very much. And if you have some questions, we can stop now and go to your questions or comments.
Yes, thank you, Professor Glicksman. We'd like to start the Q&A period. If you have any questions, please feel free to post them in the chat window or use the raise your hand function, and I will unmute you and you can ask your question directly. We do have a question from Jonathan Rayum. He asks, how does one get the manufacturers of HVAC equipment and the energy companies on board?
Well, the answer to that is some of those companies actually are getting on board. Again, I guess it's a question of developing the demand for these types. There are two solutions. One is the developing demand. So we have to educate the consumers, and consumers being both people, individuals in residential units as well as in large buildings, to demand more things. At the same time, although I'm not always an advocate of this, I think we really have to think about more stringent codes. Codes actually have been very successful in some areas. For example, in refrigerators, the advent of codes by California and then by U.S. have substantially improved the efficiency of refrigerators, so that now the refrigerator uses only about a third as much energy as they used about 25 years ago. Same kind of things will be available here. As we develop new technologies, and as we prove that they are economically viable and they are technically feasible, we need to start pushing the manufacturers to start moving in that direction. Well, maybe I can ask a question of you people. This is my usual technique. If the class is not asking too many questions, how many of you have thought about really some energy efficiency retrofits for your home? Have any of you seriously invested in things?
Dwight Blaha said, yes, having some home energy assessment done.
Oh, that's great. And in fact, that is really the first step, is to get a good professional to come in and give you some advice of what makes sense. And again, a lot of things that people are pushing, for example, replacing windows, may not be the first thing you want to do. You might want to, if you have an unfinished attic, is go in and add some insulation in the attic, find some way of sealing up the leaks around your house, possibly having somebody come in and do a tune-up on your heating and cooling system as a way of increasing efficiency.
Hello, Shafali Hill, you have a question?
Yes, I do. I really enjoyed the presentation, and one of the things it made me think about was that it seems like to date, a lot of the conversation around energy efficiency has been more philosophical, whereas you've really focused on the cost benefit for it. And I was wondering if you're seeing that, you know, kind of to your question about how many people have actually had anything done to their home. I think most people on a day-to-day basis think more about cost than they do about energy efficiency. And I was just wondering if there are things happening to kind of get that message out both into industry and to residential people that there are actually cost benefits that you'll get.
Well, in many cases, that is a tough message to get out to people. For individuals, again, you may notice that, at least up here in the Boston area, during the wintertime and even spring, we get bombarded with commercials from people offering to sell us new windows to increase energy efficiency. And as I said, that's probably not the first thing to be done, and actually, after you probably get an estimate of how much it costs to replace the windows, that's probably the end of the story. You generally don't do it. It's interesting, though, in industry now, they are starting to get the message. For example, in some of the retail spaces, and of all people, Walmart has been one of the people who've been very serious about energy efficiency in some of their stores. Have tried out some things, have actually published the results so that other people can look at it. And I've heard from some other people, who have large box stores that they have gradually started instituting energy efficiencies and found out that in fact, they're paying off. I think the problem here, though, again, is these people view this now as maybe even a commercial advantage, and they're not, although they'll go to technical conferences and talk in generalities, it's awful hard to get the cost benefits. Here on campus, I'm also involved in the Campus Energy Task Force to see what we can do here on campus. We actually have a challenge grant from NSTAR, our local electrical utility, to make some energy efficiency improvements and reduce our electricity consumption. And we're determined as we do this to post the results, both in terms of the technical results, how much energy did we save, as well as what did it cost, so people could understand the cost benefits for some of these things. And some of these, the payback period could be as short as 6 months for some of the things that we're doing. But again, it's a tough story to tell people and to get the right story out for these. And this has really been a challenge as we go forward in this.
I'll take a moment to answer a question here that Chang Zhang asked. Will the slides be available for download? And they will be. Actually, would you like to provide the slides along with the video?
Sure, no problem.
Yes, there will. A video presentation of this seminar will be available from the same site where you found out about it and where you registered. Jonathan Rayum has another question, which is, we've all heard of green roofs. How about green walls?
Well, there are people who are looking at them. Frankly, we did this study of green roofs. I didn't emphasize that in the comparison, but it turns out that green roofs in many cases, don't buy you very much either. There are some advantages if you talk about an uninsulated roof, because simply adding some soil to the roof adds into the insulation effect. But green roofs are probably about the same as cool roofs in terms of their impact, although you do get, in some cases, people have put green roofs and now have a livable, outdoor space that they can use. In that case, there are some other positive effects of the green roof. I've heard of some architects talking about green walls, but I haven't really seen any real practical embodiments of it. I guess the most practical embodiment is if you go up to Harvard, you'll find ivy on the walls of some of their buildings, but not enough that has any effect. It's certainly something interesting to think about in the future, but to date, I have not come up with any ideas or seen anything that would cause me to say, boy, this is really a major contribution to solving our problems.
Great. Dwight Blaha asks, how can we get the builders more engaged? You mentioned that the industry is fragmented. What could be some incentives to entice them to adopt energy-saving practices?
Well, again, the more we can educate the consumers to demand these types of things, I think the more the builders, and in fact, to demand that some kind of a measurement be made of what the performance of the buildings are. Every builder now says that they're making sustainable or green buildings. And in many cases, that may mean just some very modest gesture of one sort or another without really doing anything that's really substantial. I think one of the things, one of the ideas maybe we should adopt is the European Union now has a rule that for any new buildings which are sold, or in fact even buildings which change hands, there has to be a measurement given to the new owner of what the energy performance of that building is. That same kind of thing would be very helpful here in this country, so people could really understand how well buildings are performing. And I think once we start instituting things like that, the builders will probably take this a little bit more seriously. But again, there has to be the pressure from the outside for the consumer to really want this. I mean, I would say right now the characterization of someone buying a new home is, if you ask them, would you like more energy efficient windows, or would you like granite countertops in the kitchen? I think I know what the answer is for most consumers at this stage. So we need to do some education to point out this is what will be the energy savings year to year, and if you sell the house, again, there'll be some way you can get a premium on your sales price by being able to show people, in fact, that the building is more energy efficient. There have been some steps taken, but we certainly have a lot more to go in this thing.
We have another question, a more personal question from Michelle Saka. She asks, is your own home very energy efficient, and what types of things have you done to your own home?
Well, as a matter of fact, there's a number of things I've done. When I first moved into the house, I crawled up in the attic with my son, and we put insulation, a large amount of insulation in the attic. Had very little when we first moved in. And I must say, the first thing we noticed was in the summertime it was much more comfortable because we reduced the amount of heat that came in from the warm roof. Since then, we've added more insulation in the attic. We've put insulation in the exterior walls. We recently added insulation to the basement, the interior of the basement. And in fact, I've replaced all of the windows in the house with more energy efficient windows. Interesting story there, though. When I looked at the different window types and told the builder what I wanted, he said, well, you won't be able to get a federal tax credit for particular windows because it doesn't meet the federal standard. And it turned out the federal standards had been written apparently in California. So the standards were how you could reduce the amount of solar gains to the interior of your home as a way of saving on air conditioning. But of course in Boston, you want the solar gains because most of the time what you're worrying about is heating the home rather than cooling the home. So I said, the heck with the federal standards, let's go with the windows that make the most sense. So part of the problem is even getting the federal government on board to do things which make sense.
Okay, great. Looks like that is the end of our questions. If anybody does have another question, feel free to post it as we wrap up here. I'd like to thank Professor Glicksman for the presentation and for all of you for attending. Please keep your eyes out for the June web seminar that is upcoming. And thank you very much.
Thank you.